These are the answers to the AP Chemistry packet that covers topics 9.1 to 9.7. On this slide, you can see Unit 9 at a glance. Unit 9 is entitled Thermodynamics and Electrochemistry. In this video, we will take a look at topic 9.1, Introduction to Entropy, topic 9.2, Absolute Entropy and Entropy Change, topic 9.3, Gibbs free energy and thermodynamic favorability, topic 9.4, thermodynamic and kinetic control, topic 9.5, free energy and equilibrium, topic 9.6, free energy of dissolution, and topic 9.7, coupled reactions. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 9.1, Introduction to Entropy. Here are some essential knowledge statements from the AP Chemistry course and exam description. Entropy increases when matter becomes more dispersed. For example, the phase change from solid to liquid or from liquid to gas results in a dispersal of matter as the individual particles become freer to move and generally occupy a larger volume. Similarly, for a gas, the entropy increases when there is an increase in volume at constant temperature, and the gas molecules are able to move within a larger space. For reactions involving gas phase reactants or products, the entropy generally increases when the total number of moles of gas phase products is greater than the total number of moles of gas phase reactants. Entropy increases when energy is dispersed. According to the kinetic molecular theory, or KMT, the distribution of kinetic energy among the particles of a gas broadens as the temperature increases. As a result, the entropy of the system increases with an increase in temperature. The change in entropy, or delta S, is related to changes associated with the dispersal of matter and/or energy. The following situations would result in a positive delta S, or an increase in the entropy of the system. The particles of matter are more dispersed. There is a greater number of possible arrangements of the particles. There is a greater distribution of kinetic energy among the particles. The following situations would result in a negative delta S, or a decrease in the entropy of the system. The particles of matter are less dispersed or more ordered. There is a smaller number of possible arrangements of the particles. There is a smaller distribution of kinetic energy among the particles. Now, take a look at the particle diagram on this slide. From left to right, a sample of matter is changing from a solid to a gas. The particles become more dispersed and have more freedom to move around. Therefore, the entropy of the system is increasing and the sign of delta S is positive. But if we move in the opposite direction, from right to left, where a sample of matter is changing from a gas to a solid, the particles become less dispersed and more ordered, and the entropy of the system would be decreasing and the sign of delta S is negative. So this particle diagram gives you a visual representation of the dispersal of matter. Now let's take a look at a visual representation of the dispersal of energy. So here on this slide, you can see a Maxwell Boltzmann distribution for a gas sample. And so increasing the temperature of a gas sample results in a broader distribution of the speeds and the kinetic energies of the gas particles. The entropy of the system increases with an increase in temperature. Question 1. For each of the following, indicate the sign, positive or negative, of the change in entropy, or delta S, associated with the change. For phase changes, if you are changing from a solid to a liquid, or changing from a liquid to a gas, there will be an increased dispersal of matter, and the particles are freer to move and can spread out more. So the entropy of the system would increase, leading to a positive delta S. Let's take a look at our first three examples in that table on the left. So changing from a solid to a liquid, that would be a positive delta S. Changing from a liquid to a gas would be a positive delta S. Or changing from a solid to a gas would be a positive delta S. Now, if you go in the opposite direction, so changing from a gas to a liquid, or changing from a liquid to a solid, now the matter is less dispersed and more ordered. The particles have less freedom to move and spread out, so the entropy of the system decreases, and that would be a negative delta S. So changing from a liquid to a solid would be a negative delta S. Changing from a gas to a liquid is a negative delta S, or changing from a gas to a solid is a negative delta S. Now, let's take a look at what happens when an ionic solid is dissolved in water to produce aqueous ions. If we begin with a sample of a crystalline solid and we dissolve it in water to produce aqueous ions, our prediction is the following. There should be an increased dispersal of matter. The particles are freer to move and can spread out more, so our prediction would be that the entropy of the system increases, and that would lead to a positive delta S. So if solid ammonium nitrate is dissolved in water to produce the aqueous ions, ammonium and nitrate, our prediction would be that the entropy should increase, leading to a positive delta S. What happens if we go in the opposite direction? So suppose we start with aqueous ions and a precipitate is formed, leading to a crystalline solid. Now, we would predict that matter is less dispersed and more ordered, that the particles have less freedom to move and spread out, therefore the entropy of the system should decrease, leading to a negative delta S. So when aqueous ions of silver and chloride come together to form a solid silver chloride precipitate, we would predict that the change in entropy would be negative. Now let's take a look at our next example. We have a chemical reaction represented by a balanced chemical equation. So to make a prediction about the sign of delta S associated with this chemical reaction, let's compare the phases of matter on each side of this chemical equation. So on the left, for the reactants, we have 2 moles of solid. And on the right, for the products, we have 2 moles of solid and 3 moles of gas. So our prediction is the following. There should be an increased dispersal of matter. The particles are freer to move and can spread out more. That would lead to an increase in the entropy of the system and a positive delta S. Now, in our next example, we have a different chemical reaction represented by a balanced chemical equation. Let's do the same analysis and focus on the phases of matter on each side of this chemical equation. So on the left, for the reactants, we have 4 moles of solid and 3 moles of gas. And on the right, for the products, we have 2 moles of solid. So our prediction for this chemical reaction is that the matter is less dispersed and more ordered. The particles have less freedom to move and spread out. That would lead to a decrease in the entropy of the system and a negative delta S. Now, for these last 2 examples of chemical reactions, you will notice that as we proceed from the reactants to the products, we're not changing the phase of matter at all. We start with gaseous reactants, and we end with gaseous products. But what we are changing is the total number of moles of gaseous particles. So in this example, we start with 1 mole of gas for the reactants, and we end with 2 moles of gas for the products. So as a result of this change, there should be a greater number of possible arrangements because of the increase in the total number of moles of gaseous particles. This would result in an increase in the entropy of the system and a positive delta S. And as I mentioned earlier for that essential knowledge statement, it says, for reactions involving gas phase reactants or products, the entropy generally increases when the total number of moles of gas phase products is greater than the total number of moles of gas phase reactants. So if we go in the opposite direction, so in this last example, we start with 4 moles of gas for the reactants, and we end with 2 moles of gas for the products. So as a result of decreasing the total number of moles of gaseous particles, there should be a smaller number of possible arrangements, a decrease in the entropy of the system, and a negative delta S. So now that we're done with question 1, let's move on to question number 2. Particulate representations for 2 different processes are shown above. Indicate whether the entropy of the system decreases or increases for each process. Justify your answers in terms of the arrangement of the particles. So looking at process number 1, it appears from the information in that diagram that it's changing from a solid to a gas. There's an increased dispersal of matter. The particles are freer to move and can spread out more. So the entropy of the system increases with a positive delta S. And for process number 2, it looks like we have a gas both before and after the change, but we start with 4 gas particles and it changes to 2 gas particles. So there's a smaller number of possible arrangements as we decrease the total number of gas particles. So the entropy of that system decreases with a negative delta S. All right, this is question 3. It says the diagram above shows 2 different Maxwell Boltzmann distributions of kinetic energies. These 2 curves represent identical samples of helium gas at 2 different temperatures. On this slide, I'm showing you information from an earlier topic. This is from Unit 3, and this is topic 3.5, Kinetic Molecular Theory. And one of the essential knowledge statements says that the KMT relates the macroscopic properties of gases to motions of the particles in the gas. It says the Maxwell-Boltzmann distribution describes the distribution of the kinetic energies, also the speeds, of particles at a given temperature. And on this slide, this was from an earlier video where I was giving you 2 different Maxwell-Boltzmann distributions, and you had to decide which curve represents the higher temperature. So you can see these are already labeled, that the gas sample at the higher temperature has a broader distribution of particle speeds. This is also true for kinetic energies. So now back to this question from this packet, number 3, the dashed curve would represent the higher temperature. So part A of question 3, the curve represented by the dashed line represents the sample that is at a higher temperature. Part B, when the temperature of a gas sample is increased, this results in a broader distribution of kinetic energies. Part C, a broader distribution of kinetic energies is associated with a greater dispersal of energy. Therefore, when the temperature of a gas sample is increased, the entropy of the gas sample increases. Now it's time to look at the next topic in this packet. This is topic 9.2, absolute entropy and entropy change. Here is an essential knowledge statement from the AP Chemistry course and exam description. The entropy change for a process can be calculated from the absolute entropies of the species involved before and after the process occurs. So in this equation, it says that the standard change in entropy for a reaction is equal to the sum of the absolute entropies of the products minus the sum of the absolute entropies of the reactants. Now, if this equation looks similar or familiar to things you've seen before, it is. Back in topic 6.8, you learned about the enthalpy of formation. And you learned that the standard enthalpy change for a reaction or a process occurring at standard conditions is equal to the sum of the standard enthalpy of formation for the products minus the sum of the standard enthalpies of formation for the reactants. So we learned that at standard conditions, the gas pressure is 1 atmosphere, the solution concentration is 1 mole per liter, and the temperature is equal to 25 degrees Celsius or 298 Kelvin. Now, if you take a look at the AP Chemistry equations and constant sheet, and this is the section entitled Thermodynamics and Electrochemistry, you will see that the first 2 equations that are listed were actually studied back in Unit 6. Unit 6 is entitled Thermochemistry. So that first equation, Q equals mc delta T, you would use that equation involving the change in temperature of a pure substance, where you know the specific heat capacity, or in general, if you're doing any kind of calorimetry calculations. And then the next equation involving products minus reactants, you would use that equation if you were given a table of standard enthalpies of formation for various substances in a chemical reaction, and that would give you the change in enthalpy, the standard change in enthalpy for a reaction. And then now, here in topic 9.2, absolute entropy and entropy change, you can do a similar products minus reactants calculation, but this time you're calculating not the delta H, but the delta S, the change in entropy, the standard change in entropy for a reaction. And then when we get to topic 9.3, Gibbs free energy and thermodynamic favorability, we will see the next two equations that are listed in this section. So there's a similar products minus reactants equation involving the standard free energy, or delta G. And then you will definitely talk about the delta G, the standard free energy change, is equal to the enthalpy, delta H, minus T delta S, where a delta S is the change in entropy. So these two equations will be featured in topic 9.3. Now let's get back to this particular equation in topic 9.2. So again, here is the equation. The quantity S with that superscript 0 represents the standard molar entropy for a substance at standard conditions. And again, they are defined as gas pressure 1 atmosphere, solution concentration 1 mole per liter, and temperature equal to 25 degrees Celsius or 298 Kelvin. So the absolute entropy of a substance is normally reported in units of joules per Kelvin mole. The standard entropy change for a physical or chemical change, delta S with that superscript 0, is normally reported in units of joules per Kelvin mole of reaction. Now, before we take a look at question 4 in the packet, I just want to make an important distinction between the standard enthalpy of formation for an element and the standard molar entropy of an element. So back in topic 6.8, enthalpy of formation, you learned that the standard enthalpy of formation for an element in its standard state is equal to 0. However, the standard molar entropy of an element in its standard state is not equal to 0. All right, let's take a look at question 4. In part A, it says, use the data in the table at right to calculate the value of the standard entropy change, or delta S, in units of joules per Kelvin mole of reaction for the reaction represented by the following equation. So in this equation, we have CaCO3 solid, that's calcium carbonate, and it's decomposing to solid calcium oxide, CaO, and carbon dioxide gas. So we'll use the equation, products minus reactants, and we are given the standard molar entropy for each substance in this reaction. So it's going to be 38.1, which is for calcium oxide, plus 213.8 for carbon dioxide, minus 92.9 for calcium carbonate. When we do this math on our calculator, we get positive 159, and the units are joules per Kelvin mole of reaction. Part B says, how does the entropy of the system change as this reaction occurs? Well, let's take a look at what's changing in terms of phases of matter. So we start with 1 mole of solid in the reactants. And then for the products, we have 1 mole of solid plus 1 mole of gas. So even if you hadn't done the calculation, you might already anticipate that we're going to have an increase in the entropy. So when you see a positive delta S for a reaction or a process, that means that the entropy is increasing for the system. All right, now let's take a look at question 5 in the packet. You can see it's going to be a similar calculation, but we have a different chemical equation to process. So in this equation, we start with 2 moles of nitrogen monoxide gas, or NO, reacting with 1 mole of molecular oxygen gas, O2, and it produces 2 moles of nitrogen dioxide gas. Notice that we have the standard molar entropy for all 3 substances listed in the table, and as I had mentioned earlier, the standard molar entropy for an element, such as O2, is not 0. So in the table, you can see it's 205 joules per Kelvin mole. Let's go ahead and use our equation for products minus reactants to calculate the value of delta S. So it's going to be 2 times the number for nitrogen dioxide. So 2 times 240, that's the products, and then minus 2 times the number for nitrogen monoxide, so 2 times 210.7, and also plus 205. So if I do this math on my calculator, I get a value of negative 146.4, and the units are joules per Kelvin mole of reaction. Even if you hadn't done the calculation, you might anticipate there's going to be a decrease in entropy. So we start with 3 moles of gas for the reactants, and we end with 2 moles of gas for the products. So part B, how does the entropy of the system change as this reaction occurs? The entropy decreases. So when you see a negative value for delta S for a process or a chemical reaction, then the entropy decreases. Now it's time to move on to our next topic in the packet. This is topic 9.3, Gibbs free energy and thermodynamic favorability. And there are several essential knowledge statements from the AP Chemistry course and exam description. The Gibbs free energy change for a chemical process in which all of the reactants and products are present in a standard state, as pure substances, as solutions of 1 molar concentration, or as gases at a pressure of 1 atmosphere or 1 bar, is given the symbol delta G with that superscript 0. The standard Gibbs free energy change for a chemical or physical process is a measure of thermodynamic favorability. Historically, the term spontaneous has been used to describe processes for which the standard Gibbs free energy change is negative. The phrase thermodynamically favored is preferred instead, so that common misunderstandings equating spontaneous with suddenly or without cause can be avoided. So when the standard Gibbs free energy change is negative for a process, it is said to be thermodynamically favored. The standard Gibbs free energy change for a physical or chemical process may also be determined from the standard Gibbs free energy of formation of the reactants and products using the equation the standard Gibbs free energy change is equal to the sum of the Gibbs free energy of formation for the products minus the sum of the Gibbs free energy of formation for the reactants. And here you can see, as I had mentioned earlier in this video, this equation involving products minus reactants to calculate the standard free energy change for a reaction. This is one of the equations that is featured on the AP Chemistry equations and constant sheet. In some cases, it is necessary to consider both enthalpy, which is delta H, and entropy, delta S, to determine if a process will be thermodynamically favored. The freezing of water and the dissolution of sodium nitrate are examples of such phenomena. Knowing the values of the enthalpy change, delta H, and the entropy change, delta S, for a process at a given temperature allows the free energy change, or delta G, to be calculated directly. And the equation delta G equals delta H minus T delta S, that is also featured on the AP Chemistry equations and constant sheet. In general, the temperature conditions for a process to be thermodynamically favored, where delta G is negative, can be predicted from the signs of delta H and delta S, as shown in the table below. So, considering the fact that the sign of delta H could be either positive or negative, and the sign of delta S could be either positive or negative, that gives us 4 different situations, and they're listed here in this table. I'm not going to go over all 4 of these situations right now, but later in the video, between questions 11 and 12 in the packet, we will explore all 4 of these possibilities. And here you can see that the equation delta G equals delta H minus T delta S is listed on the AP Chemistry Equations and Constants sheet. I'd like to consider two of the possibilities looking at the sign of delta H and the sign of delta S, in which no calculation is necessary to determine the sign of delta G. So here's the first situation. Suppose that the sign of delta H is negative, in that we have an exothermic process. And suppose that the sign of delta S is positive, so we have a process in which entropy is increasing. Under these conditions, the sign of delta G must be negative. So as it says here, highlighted on this slide, in cases where delta H is negative and delta S is positive, no calculation of delta G is necessary to determine that the sign of delta G is negative and the process is thermodynamically favored. Here's another situation. Suppose that the sign of delta H is positive. So we have an endothermic process. Suppose that the sign of delta S is negative. So we have a process in which the entropy is decreasing. Under these conditions, the sign of delta G must be positive. So in cases where delta H is positive and delta S is negative, no calculation of delta G is necessary to determine that the sign of delta G is positive and the process is thermodynamically unfavored. Now, before we take a look at question 6 in the packet, let me just summarize what free energy represents. The free energy of a system represents the amount of work that the system can perform on the surroundings. So if the change in free energy, or delta G, for a certain process is negative, then the forward process from left to right is thermodynamically favored to occur. And the magnitude of delta G represents the amount of energy released when the forward process occurs. And this energy is free or available to do work on the surroundings. On the other hand, if the change in free energy, or delta G, for a certain process is positive, then the forward process from left to right is not thermodynamically favored. Instead, the reverse process from right to left is favored. So the magnitude of delta G represents the amount of energy that must be transferred from the surroundings to the system in order for the forward process to occur. This is question 6. In part A, it says use the data in the table at right to calculate the value of the standard free energy change, delta G, in units of kilojoules per mole of reaction for the reaction represented by the following equation. And this is the decomposition of calcium carbonate. We've seen this exact equation earlier in the packet back in question 4. But now, instead of calculating the change in entropy, delta S, we're calculating the change in free energy, delta G. So in the table, we're given the free energy of formation for each substance in this chemical equation. So let's begin this calculation. We're going to use this particular equation involving products minus reactants, and we're going to use the data from the table for the standard free energy of formation for each substance. So here is our equation, products minus reactants, and for the products it would be calcium oxide and carbon dioxide. So it's going to be negative 603.3 for solid calcium oxide, plus the number for carbon dioxide, which is negative 394.4, and then minus the delta G for calcium carbonate, which is negative 1,128.8. So when we do this math to calculate the value of delta G, we get positive 131.1 kilojoules per mole of reaction. Now, is this reaction thermodynamically favored under standard conditions? And the answer is no, because the sign of delta G for this reaction is positive. Now let's take a look at question 7, which is very similar to question 6. And this reaction in question 7 should look familiar to you. We saw this same equation back in question 5 of the packet. But unlike question 5, where we were calculating the change in entropy, or delta S, here in question 7, we're calculating the standard free energy change, delta G. So we are given the free energy of formation for nitrogen monoxide, NO, and for nitrogen dioxide, NO2. But just like the enthalpy of formation, delta H of formation, the free energy of formation is defined to be 0 for an element in its standard state, like O2. So that's why the value for O2 is 0. Let's go ahead and use the products minus reactants equation. And we have one product would be 2 moles of NO2. So it's going to be 2 times the number for NO2, which is 51.3. And then we have minus the reactants. Well, one of them is 0, but it's going to be 2 times the number for nitrogen monoxide. That's 2 times 86.6. When we do this math, we get the delta G for this reaction, and it's negative 70.6 kilojoules per mole of reaction. So part B asks, is this reaction thermodynamically favored under standard conditions? And now the answer is yes, because the sign of delta G for this reaction is negative. Now, let's move on to question 8. Above question 8, it says the Gibbs free energy equation is shown above. The Gibbs free energy equation is delta G equals delta H minus T delta S. The variable T refers to the absolute temperature in units of kelvins. The degree symbol refers to a process that occurs at standard conditions. So this is question 8. It says, consider the information shown above. Which of the following statements best explains why this reaction is not thermodynamically favored under standard conditions? So we are given the value of delta G, delta H, and delta S for this equation. We know that because the sign of delta G is positive, that means that this reaction is not thermodynamically favored under standard conditions. But let's focus on, is it the change in enthalpy, delta H, or is it the change in entropy, delta S? Which one of these values, or which one of these quantities, best explains why this reaction is not thermodynamically favored? So as we process the Gibbs free energy equation, we know that a physical or chemical process is thermodynamically favored when delta G for the forward process is negative. So what values for delta H and delta S would make the sign of delta G negative? Well, if we have an exothermic process that has a negative value for delta H, this does support the favorability of a process. And what about delta S? Well, if we have a positive delta S, a process in which the entropy increases, then this also would support the favorability of a process. Now, let's take a look at question 8. So we know that the delta H for this reaction is positive, and that the delta S for this reaction is also positive. But since this reaction is not thermodynamically favored under standard conditions, it must be the change in enthalpy that does not support favorability. So what does support favorability of a reaction or a process is a negative delta H and a positive delta S. So when you have a positive delta H, as we do in this example, that would not support the favorability of a reaction or process. Now let's take a look at question 9. In question 9, we are given a chemical equation and we have the value of delta G, delta H, and delta S. It says, consider the equation or the information shown above. Which of the following statements best explains why this reaction is thermodynamically favored under standard conditions? So now for this reaction, the sign of delta G is negative. So we know it is favored. So is it a negative delta H or is it a positive delta S that would best explain why this process is favored? Well, considering the delta H is negative and the delta S is negative, it is a negative delta H that does support the favorability of a reaction, but a negative delta S does not support the favorability of a reaction. Now, before we look at question 10 in the packet, I'd like to talk about driving forces that support the thermodynamic favorability of a process. You can think of a driving force as a feature of a physical or chemical process that helps to explain why that process is thermodynamically favored to occur. And there are two possibilities for a driving force. If the process is exothermic, that is, the sign of delta H is negative, then this could be a driving force to explain why the process is thermodynamically favored to occur. In addition, if the process involves an increase in entropy, that is, the sign of delta S is positive, this also could be a driving force to help explain why the process is thermodynamically favored to occur. Another way to think about the driving force of a process is to look at the signs of delta H and delta S for that process. Ask yourself the following question. Does the sign of delta H or delta S cause the value of delta G to be negative? Remember, a negative delta G is associated with a thermodynamically favored process. So, a negative delta H and a positive delta S are associated with driving forces to explain why a process is thermodynamically favored to occur. Finally, if the process is endothermic, that is, the sign of delta H is positive, then this cannot be a driving force to explain why the process is thermodynamically favored to occur. In addition, if the process involves a decrease in entropy, that is, the sign of delta S is negative, this also cannot be a driving force to explain why the process is thermodynamically favored to occur. So now that I've taken a look at driving forces that support the thermodynamic favorability of a process, let's take a look at questions 10 and 11 in the packet. Question 10 says, the process represented by the equation above is thermodynamically favored to occur at 298 kelvins. The chemical equation features ammonium nitrate, NH4NO3, solid on the left, and on the right features aqueous ions of ammonium and nitrate. When a small amount of solid ammonium nitrate is added to a sample of water and the mixture is stirred, all of the solid dissolves. Again, that's consistent with the fact that this process is thermodynamically favored to occur. It also says the temperature of the solution decreases. That's an important detail because that observation will help us decide if this is an endothermic or exothermic process. It says, answer the following questions related to the process of dissolving solid ammonium nitrate in water. Part A. The sign of delta H for this process is. So the temperature of the solution decreases. That means it's going to be an endothermic process in which heat energy or thermal energy is absorbed from the surroundings. Otherwise, if it were exothermic, then heat would be released and the temperature of the solution would increase. So because the temperature of the solution decreases, we have an endothermic process, and the sign of delta H for an endothermic process is positive. Now, part B, the sign of delta S for this process. We can assume that if we start with 1 mole of solid and it dissociates in aqueous solution to produce 2 moles of aqueous ions, we would predict that because there's a dispersal of matter in which the particles have more freedom to spread out and move around, that this would be an increase in the entropy of the system, and that would be a positive delta S. Now, part C, what is the driving force for this process? Is it enthalpy only, entropy only, or both enthalpy and entropy? Remember that we're looking for something that would support a negative delta G. So the driving forces are negative delta H, which we do not have in this example, and positive delta S, which we do have in this example. So this would be entropy only. That would be the driving force for this example. Now let's take a look at question 11. In question 11, it says the process represented by the equation above is thermodynamically favored to occur at 298 kelvins. This is 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to produce 2 moles of water vapor. A mixture of hydrogen gas and oxygen gas is sparked to initiate a chemical reaction. Water vapor is produced and heat and light are released. So that detail, that heat and light are released, will help us make a decision about the sign of delta H for this process. Answer the following questions related to this chemical reaction. Part A. The sign of delta H for this reaction is, well, because heat and light are released, that would be an exothermic process, and we know for an exothermic process, the sign of delta H is negative. Now for entropy, we start with a total of 3 moles of gaseous reactants, and then we finish on the other side of the equation with 2 moles of gaseous products. So because of that decrease in the total number of moles of gas in this reaction, that will result in a decrease in the entropy. So a decrease in entropy would be a negative delta S. Now, part C, what is the driving force for this process? Is it enthalpy only, entropy only, or both enthalpy and entropy? Remember that we're looking for what would cause the sign of delta G to be negative. That's going to be a negative delta H, which we do have in this example, and a positive delta S, which we do not have in this example. So it's going to be enthalpy only as a driving force in this example. Now, earlier in this video, when I was introducing topic 9.3, Gibbs free energy and thermodynamic favorability, I had mentioned this table in which there are 4 different situations, depending on if the sign of delta H is positive or negative, and whether the sign of delta S is positive or negative. So there's 4 different situations. Let's take a look at the details of each of these 4 situations. So from left to right in this table, I have delta H, which is either positive or negative, and what that means. I have delta S, which is either positive or negative, and what that means. Then I have the question, is the forward process thermodynamically favored? And then finally, what is the driving force that justifies why the reaction or the process is thermodynamically favored? So our first situation looks like this. We have a positive delta H, and the meaning of that would be an endothermic process. We have a negative delta S, and the meaning of that is that the entropy of the system decreases. And if you look at the Gibbs free energy equation at the top of the slide, you can see that if delta H is positive and delta S is negative, then mathematically delta G must be positive. Therefore, is the forward process thermodynamically favored? And the answer is no, it's not favored at all at any temperature, no matter what. In fact, the reverse process from right to left would be thermodynamically favored. Now, here's our next example. Now, what if the delta H has a negative sign? That means we have an exothermic process. What if the delta S has a positive sign? That means that the entropy of the system increases. Well, now, mathematically, if we have a negative delta H and a positive delta S, then delta G must have a negative sign. And that would be thermodynamically favored at all temperatures. The driving force would be both the enthalpy delta H and the entropy delta S. Now in the next example, both the delta H and the delta S are positive. So that means we have an endothermic process in which the entropy of the system increases. Well, now we don't know for sure what the sign of delta G is. It's going to be temperature dependent. So at low temperatures, the delta G should be positive, and therefore the reaction would not be thermodynamically favored. But at high temperatures, now the delta G for this process would be negative, and it would be thermodynamically favored. So it's favored at high temperatures. But because we have a positive delta H, that cannot be a driving force. So the driving force would be the entropy only, the positive delta S only. And now in our last situation, both the delta H and the delta S are negative. So that means we have an exothermic process where delta H is negative, and we have a process in which the entropy of the system decreases, so delta S is negative. What's the sign of delta G? Well, it depends on the temperature again. So if there is a low temperature, then delta G should be negative and the process should be favored. But if the temperature is high, then the sign of delta G would be positive and the process would not be favored. So if it does occur, it's going to be driven by enthalpy only. A negative delta S cannot be a driving force, but only this negative delta H would be the driving force. All right, we're now going to see examples in questions 12, 13, 14, and 15 in this packet that consider all four of these possibilities. So this is question 12. Question 12 says, answer the following questions related to the reaction represented by the equation shown above. Part A, use the data in the table at right to calculate the value of the standard enthalpy change, delta H, in units of kilojoules per mole of reaction for the reaction represented by the equation shown above. So in the table, we are given values for the standard enthalpy of formation. Let's use the products minus reactants equation, where delta H of formation is given for all four substances in this chemical equation. So it's going to be products minus reactants. That's going to be the number for C6H12O6, which is negative 1274.4, plus 6 times the number for oxygen, which happens to be 0. Those are our products. And then minus the sum of the enthalpy of formation for the reactants. That would be 6 times the number for CO2, which is negative 393.5, plus 6 times the number for H2O, which is negative 241.8. We do all of that math and we get positive 2,537.4 kilojoules per mole of reaction. Now, moving on to part B of this question, it's going to be a similar process in that we're going to use a products minus reactants equation, but this time, instead of solving for the delta H, we're solving for the delta S. So in the table, we are given the value for the standard molar entropy for each substance. So products minus reactants looks like this. We have the number for C6H12O6, which is 212.1. We have 6 times the number for O2, which is 205. Those are our products. And then minus the sum of the standard molar entropies for the reactants. It's going to be 6 times the number for CO2, so 6 times 213.8, and then plus 6 times the number for water vapor, which is 188.8. So we do all of that math, and our delta S works out to be negative 973.5, and the units are joules per Kelvin mole of reaction. So in part A, we calculated the delta H for this reaction under standard conditions, and in part B, we calculated the delta S under standard conditions for this reaction. Now, in part C, it says, use the Gibbs free energy equation and your answers to parts A and B to calculate the value of the standard free energy change, delta G, in units of kilojoules per mole of reaction for the reaction represented by the equation shown above. The temperature at standard conditions is 298 kelvins. Pay attention to the units in your calculations. The units of delta H, which are kilojoules per mole of reaction, are different than the units of delta S, which are joules per Kelvin mole of reaction. So if I take the Gibbs free energy equation, which looks like this, delta G equals delta H minus T delta S, and I look at my answers to part A and B, and I just plug them in. So for delta H, it's positive 2,537.4. I've got my temperature, 298 kelvins, and then I plug in my answer to part B, negative 973.5. If I set up the calculation like this, or if you set up the calculation like this, then this setup would give you the wrong answer. Why? Because we didn't pay attention to the units in this calculation. So as I mentioned, the units of delta H, which are kilojoules per mole of reaction, are different than the units of delta S, which are joules per Kelvin mole of reaction. So how are we going to resolve this problem with different units? Well, the instructions in part C said to calculate the value of delta G in units of kilojoules per mole of reaction. So I'm not going to change the units of delta H because they already are in units of kilojoules per mole of reaction. But I have to change from joules to kilojoules with the delta S. So what I'm going to do for my answer to part B is I'm going to divide by 1,000. So if I multiply by a conversion factor to go from joules to kilojoules, 1 kilojoule over 1,000 joules, this will help to resolve that difference in units. So when I do that math, it becomes a delta S of negative 0.9735, and now my units are kilojoules per Kelvin mole of reaction. Now I can plug in those values into the Gibbs free energy equation, and my units will work out. So the kelvins will cancel. I'm doing 298 Kelvin times negative 0.9735 kilojoules per Kelvin mole of reaction. So the Kelvin will cancel out, and my answer, when I do this math, is going to be in the proper units of kilojoules per mole of reaction. So I happen to get a value on my calculator when I did this math of positive 2,827.5. Part D, is this reaction thermodynamically favored at 298 Kelvin? And the answer is no, because the sign of delta G is positive. Now, part E says, circle the situation that best describes this reaction. Not favored at any temperature, favored at all temperatures, favored at high temperatures, or favored at low temperatures. Focus on the sign of delta H and the sign of delta S, and you can figure out what's going on. So the sign of delta H is positive. The sign of delta S is negative. Let's go back to that table that I had mentioned earlier in the video and see where this situation fits. So positive delta H, negative delta S, that would mean that this process or this reaction is not favored at any temperature. So that is our answer to part E. Now, let's move on to question 13. In question 13, we have a different chemical reaction to analyze, but the calculations that we're going to be doing in question 13 are very similar to the calculations that we did in question 12. So here in part A, it says use the data in the table at right to calculate the value of the standard enthalpy change, delta H, in units of kilojoules per mole of reaction for the reaction represented by the equation shown above. Now in the table, we have 4 different substances, but since 2 of them, oxygen O2 and nitrogen N2, are elements in their standard states, then by definition they have a standard enthalpy of formation of 0. Let's go ahead and use the products minus reactants equation to calculate delta H, just like we did in question 12, part A. So for the products, it would be the number for nitrogen, which happens to be 0, plus 2 times the number for water vapor, which is negative 241.8. So those are the products. And then minus the sum of the enthalpy of formation for the reactants. It's going to be 95.4, which is the number for N2H4, and then plus 0, which is the number for oxygen O2. When we do this math, we get the answer to part A, which is the delta H for this reaction, and it works out to be negative 579.0, and the units are kilojoules per mole of reaction. Now, in part B, we're going to use the data for standard molar entropy to calculate the change in entropy, or delta S. We're going to use the products minus reactants equation, just like we did in number 12, part B. So for products minus reactants, it's going to be 191.5, which is the number for nitrogen, plus 2 times the number for water vapor, which is 188.8. Those are the products. And then minus the sum of the entropy values for the reactants. So 238.5, which is the number for N2H4, plus 205.0, which is the number for O2. And when we do this math, we get that the delta S for this reaction under standard conditions is positive 125.6, and the units are joules per Kelvin mole of reaction. Now that we've answered part A, which was delta H, and part B, which is delta S, we can use the Gibbs free energy equation in part C and our answers to parts A and B to calculate the value of the standard free energy change, or delta G, in units of kilojoules per mole of reaction for this reaction. But this time, we are going to pay attention to the units in our calculations and not make any mistakes. So we're looking for units of kilojoules per mole of reaction, which means we're not going to change the units of delta H, but we have to do the same thing that we did in question 12, and that is convert from joules to kilojoules for the entropy value. So positive 125.6 joules per Kelvin mole of reaction divided by 1,000, now that becomes positive 0.1256, and the units are kilojoules per Kelvin mole of reaction. Let's plug those numbers into the Gibbs free energy equation. So negative 579 minus 298, which is the temperature, times positive 0.1256. We do this math, and we get a delta G of negative 616.4, and the units are kilojoules per mole of reaction. So is this reaction thermodynamically favored at 298 kelvins? And the answer is yes, because the sign of delta G for this reaction is negative. In part E, circle the situation that best describes this reaction. Not favored at any temperatures, favored at all temperatures, favored at high temperatures, or favored at low temperatures. Let's focus on the sign of delta H, which happens to be negative, and the sign of delta S, which happens to be positive. Let's go back to that table and see what happens when you have a negative delta H and a positive delta S. So that would mean that this process is favored at all temperatures. So that is the answer to part E. Now let's move on to question 14. So here in question 14, we have a different chemical reaction to analyze, but the calculations that we will do in question 14 are very similar to the calculations we did in questions 12 and 13. So here in part A, we're going to use the data for standard enthalpy of formation for each substance to get the value of delta H. We'll use the products minus reactants equation. So it's going to be the number for carbon monoxide, CO, which is negative 110.5, plus 2 times the number for hydrogen, which, because it's an element, happens to be 0. So those are the products. And then minus, for the reactant, we have CH3OH, and that number is negative 200.7. So when we do this math for products minus reactants, we get a delta H for this reaction under standard conditions of positive 90.2 kilojoules per mole of reaction. Now, on to part B, where we're going to calculate the delta S, the change in entropy. We're still going to use the products minus reactants equation. We're given the data for the standard molar entropy of each substance. So 197.7, which is the number for CO, 2 times the number for hydrogen, which is 130.6, and then minus the number for CH3OH, which is 239.9. So we get a delta S of positive 219.0, and the units are joules per Kelvin mole of reaction. So now that we have our delta H from part A and our delta S from part B, we're going to use those values and the Gibbs free energy equation to calculate delta G. Let's not forget about the units. So we have delta H, which is in units of kilojoules per mole of reaction. We have delta S, which is in units of joules per Kelvin mole of reaction. Let's divide by 1,000, like we did in questions 12 and 13. So the value for delta S with the proper units would be positive 0.2190 kilojoules per Kelvin mole of reaction. Let's plug in our numbers into the Gibbs free energy equation. So 90.2, which is our delta H, minus 298 times positive 0.2190, which is our value for delta S. And when we do this math, we get a delta G of positive 24.9 kilojoules per mole of reaction. So is this reaction thermodynamically favored at 298 kelvins? And the answer is no, because the sign of delta G at this temperature is positive. Now I say at this temperature because as we consider part E, is this reaction going to be favored at high temperatures or low temperatures? The sign of delta H is positive. The sign of delta S is also positive. Let's go back to that table. And when delta H and delta S are both positive, then the process or the reaction would be favored at high temperatures. So if it's favored at high temperatures, let's see if we can verify that. Let's take a look at part F of question 14. So in part F, it says use the Gibbs free energy equation and your answers to parts A and B to calculate the value of delta G in units of kilojoules per mole of reaction, but this time not at 298 kelvins, but at temperatures of 200 kelvins and 500 kelvins. Now we can assume that the values of delta H and delta S do not change significantly when the temperature is changed. So I'm going to plug in the same value of delta H that I got from part A and the same value of delta S that I got from part B, but the temperature is not 298 kelvins, now it's 200 kelvins. And when I do this math, I get positive 46.4 kilojoules per mole of reaction. All I'm going to do is change the temperature from 200 kelvins to 500 kelvins. I did not change the delta H or the delta S, I just have a new temperature. And when I do the math at 500 kelvins, watch what happens. Now the value of delta G works out to be negative 19.3 kilojoules per mole of reaction. So our prediction did come true in that it's not favored at low temperatures, but it is favored at high temperatures. So hopefully that makes sense. All right, now let us move on to question 15 in the packet. Question 15 is going to be very similar to questions 12, 13, and 14. So we have a new chemical reaction to analyze, but very similar calculations. Here in part A, we're going to calculate delta H using the products minus reactants equation. It's going to be the number for NH4Cl, which happens to be negative 314.4, minus, for the reactants, the number for NH3, which is negative 46.1, and we also have another reactant, which is HCl, and that number is negative 92.3. So when we do the products minus reactants calculation to get our delta H, we get a value of negative 176.0 kilojoules per mole of reaction. So that's our delta H in part A. Now in part B, let's calculate delta S. Again, using the products minus reactants equation, it's going to be the number for NH4Cl, which is 94.6, minus the numbers for NH3 and HCl, which are 192.5 and 186.9. So when we do that math for products minus reactants, we get a delta S of negative 284.8 joules per Kelvin mole of reaction. Now that we have our answer for delta H from part A and our answer for delta S for part B, let's go ahead and plug in the appropriate number. Again, let's make sure we don't make that mistake about units. So for delta H, it's going to be negative 176.0 kilojoules per mole of reaction. And then after we divided by 1,000 to convert from joules to kilojoules, the number for delta S is negative 0.2848 kilojoules per Kelvin mole of reaction. So we do the math, delta G equals delta H minus T delta S, and at 298 kelvins, this is what we discover. We get a value of negative 91.1 kilojoules per mole of reaction. So since our sign of delta G is negative, then yes, this reaction is thermodynamically favored at 298 kelvins. So is this favored at high temperatures or favored at low temperatures? Let's look at the sign of delta H, which happens to be negative, and the sign of delta S is also negative. So when you have a negative delta H and a negative delta S, then the reaction or the process is favored at low temperatures. Well, let's see if that prediction comes true. Is this reaction favored at low temperatures? So moving on to part F of this question, let's calculate the delta G at temperatures of 200 kelvins and 700 kelvins and see what happens. So we're assuming that the values of delta H and delta S do not change significantly when the temperature is changed. So I have my delta H, which is negative 176 kilojoules per mole of reaction. I've got a temperature of 200 kelvins, and my delta S is negative 0.2848 kilojoules per Kelvin mole of reaction. When I do this math, I get a value for delta G of negative 119.0 kilojoules per mole of reaction. But that was at 200 Kelvin. Watch what happens at 700 kelvins. I do the math. I'm not changing anything except the temperature. And now I get a value of delta G that is positive 23.4 kilojoules per mole of reaction. So yes, our prediction came true in that it is favored at low temperatures, but it is not favored at high temperatures. All right, that's the end of question 15, and now it is time to move on to the next topic in the packet. This is topic 9.4, Thermodynamic and Kinetic Control. Here are two essential knowledge statements from the AP Chemistry course and exam description. Many processes that are thermodynamically favored do not occur to any measurable extent, or they occur at extremely slow rates. Processes that are thermodynamically favored but do not proceed at a measurable rate are under kinetic control. High activation energy is a common reason for a process to be under kinetic control. The fact that a process does not proceed at a noticeable rate does not mean that the chemical system is at equilibrium. If a process is known to be thermodynamically favored and yet does not occur at a measurable rate, it is reasonable to conclude that the process is under kinetic control. So based on these two essential knowledge statements, let's take a look at question 16. We have 4 statements. Decide if each of the following statements is true or false. The first one says, if the sign of delta G for a certain process is negative, the process is thermodynamically favored to occur under standard conditions. Yes, that is true. The next one says, if the sign of delta G for a certain process is negative, the process should occur at a relatively fast rate under standard conditions. And that is false. Just because we know that delta G is negative, that only indicates that it is thermodynamically favored, but we don't know anything about the kinetics or the reaction rate for that process. It could be fast, it could be slow, but the delta G is not going to give us that information. Now, the next 2 statements have to do with the activation energy and whether the rate is fast or slow. So back during Unit 5, which was on kinetics, topic 5.6, reaction energy profile, you learned that the energy profile gives the energy along the reaction coordinate, which typically proceeds from reactants through a transition state to products. And the energy difference between the reactants and the transition state is the activation energy for the forward reaction. So on this slide, this was from an earlier video, you can see a smaller activation energy for a reaction on the left and a larger activation energy for a reaction on the right. So a smaller activation energy is associated with a faster reaction rate, and a higher or a larger activation energy is associated with a slower reaction rate. Now let's go ahead and finish up question 16. So if a certain process has a relatively high activation energy, then the process is likely to occur at a slow rate, not fast, but slow. So high activation energy, slow rate. That's why sometimes, even though a process is thermodynamically favored, if it has a relatively high activation energy, then it might be that that process occurs so slowly that you don't see anything happening or nothing is measurable. All right, now let's take a look at question 17. Here we are given a chemical equation in which nitrogen, N2, reacts with hydrogen, H2, to produce ammonia, which is NH3. We're given information about the delta H, which is negative, so it's exothermic. And we're given information about the delta G, which is negative, which means it is thermodynamically favored to occur under standard conditions. So question 17 says the following. Information about the formation of ammonia, NH3, from nitrogen and hydrogen is shown above. When equal volumes of nitrogen and hydrogen, each at 1 atmosphere, are mixed in a closed container at 298 kelvins, no formation of NH3 is observed. Select all of the following statements that represent a valid explanation for why no formation of NH3 is observed under standard conditions. The first statement says, the formation of NH3 from nitrogen and hydrogen is not thermodynamically favored to occur. Well, that's false because we know the delta G is negative, so it is favorable. So there must be something about why we are not seeing anything. Why is the reaction not seeming to occur? The next statement says that the reactants, nitrogen and hydrogen, must be combined in a 1:3 mole ratio in order for the reaction to proceed. And that's false. You can combine nitrogen and hydrogen in all kinds of ratios. You don't necessarily need that exact 1:3 ratio. And that's just true because the molecules will react until one of them is eventually consumed as a limiting reactant. But it's not like there needs to be that specific 1:3 mole ratio to get the process started. So we're thinking that even though it's favored, if there's no NH3 observed, it is probably under kinetic control, in which there is a relatively high activation energy, and that causes the rate of this reaction to be extremely slow. So that's why no formation of ammonia is observed, because it's a very slow rate because of a rather high activation energy. The last statement says that the driving force is the change in entropy. When you go from 4 moles of gas on the reactant side of the equation to 2 moles of gas on the product side of the equation, you are decreasing the number of moles of gas. Therefore, you have a smaller number of arrangements. The entropy of the system is actually going to decrease, and a negative delta S cannot be a driving force. So if delta S is negative, that cannot be a driving force. That statement is false. So why is no formation of NH3 observed, even though we have these chemicals mixed together? Most likely it's under kinetic control, where the rate of the reaction is extremely slow, and that's usually explained by a relatively high activation energy. Now let's take a look at question 18. Here we have a different chemical reaction involving hydrogen peroxide, H2O2, and it's decomposing to produce liquid water, H2O, and oxygen gas, O2. We are told that the delta H and the delta G are both negative for this reaction under standard conditions, so that means it's exothermic and it is thermodynamically favored to occur. Question 18. Information about the decomposition of hydrogen peroxide to form water and oxygen is shown above. A solution of aqueous hydrogen peroxide is typically stable for up to a year, stored in a dark bottle at 298 kelvins. When a suitable catalyst is added to the solution of hydrogen peroxide, the decomposition reaction occurs at a much faster rate. Select all of the following statements that represent a valid explanation for this observation. So it's very stable. The reaction does not seem to occur until a catalyst is added. So remember that back in Unit 5, which was on kinetics, we did talk about catalysis. That's topic 5.11. In order for a catalyst to increase the rate of a reaction, the addition of the catalyst must increase the number of effective collisions and or provide a reaction path with a lower activation energy relative to the original reaction coordinate. So we know that a catalyst generally increases the rate of a reaction by providing an alternate reaction pathway with a lower activation energy. So the addition of a catalyst has no effect on the delta G. The addition of a catalyst does not change the thermodynamic favorability or affect the value of delta G. But what it does provide is a lower activation energy through an alternate reaction pathway. So a catalyst speeds up a reaction by lowering the activation energy with a new reaction pathway. So that's why this hydrogen peroxide is pretty stable. The reaction is not seeming to occur until a catalyst is added, which speeds up the reaction by providing a lower activation energy pathway. All right, well, that is the end of question 18. So now it is time to move on to our next topic in this packet. This is topic 9.5, free energy and equilibrium. Here are some essential knowledge statements from the AP Chemistry course and exam description. The phrase thermodynamically favored, in which the value of delta G is negative or less than 0, that means that the products are favored at equilibrium, in which the equilibrium constant, which is symbolized by capital K, is greater than 1 under standard conditions. And the equilibrium constant, K, is related to free energy, delta G, by the following equations. Now, I'll just note that even though there are two equations listed here under this essential knowledge statement, only one of these equations actually appears on the AP Chemistry equation sheet, and that would be the second of these two equations. So that second equation that says delta G equals negative R times T times the natural log of K, that equation does appear on the AP Chemistry equation sheet, but that first equation is simply a mathematical rearrangement of the second equation. So if you take that second equation and you start moving some variables around, and then you want to solve for the value of the equilibrium constant K, then what you get when you rearrange that second equation is that K is equal to the letter E, and that's the base of the natural log, and then raised to a certain power. And that exponent is actually a ratio. That exponent is negative delta G divided by RT. So when we get to question 19 in this packet, I will go over all of the details about how you can use either one of these equations. So if you're given the value of K, you can solve for delta G. And if you're given the value of delta G, then you can solve for K. But just keep in mind that only the second of these two equations is actually listed on the AP Chemistry equations and constant sheet. Connections between the equilibrium constant K and delta G can be made qualitatively through estimation. So when delta G is near 0, the equilibrium constant will be close to 1. And when delta G is much larger or much smaller than the value RT, then the value of the equilibrium constant K deviates strongly from the number 1. And then finally, processes with a delta G that is less than 0 or negative would be thermodynamically favored, favoring the products, that is, the equilibrium constant K is greater than 1. And on the other hand, processes where the delta G is greater than 0 or positive, those would not be thermodynamically favored in the forward direction, so they would favor the reactants, that is, the value of the equilibrium constant K would be less than 1. So again, here on the AP Chemistry equations and constant sheet, you can see that directly below the Gibbs free energy equation that says delta G equals delta H minus T delta S, directly underneath that equation, you can see that delta G is equal to negative R times T times the natural log of the equilibrium constant K. Now, when doing calculations involving this equation, delta G equals negative RT natural log of K, I'd like you to pay attention to the following information. So first, choose the correct value of the gas constant R. That is, the R value that you should use is 8.314, and the units are joules per mole per Kelvin. So back to the AP Chemistry equations and constant sheet, now you're looking at a different section. This is the section entitled Gases, Liquids, and Solutions. And you'll notice that there's actually two values of R listed on the equation sheet. But the one that I'm highlighting with that red rectangle, that is the version that you should use when you're doing these types of calculations involving delta G equals negative R times T times the natural log of K. So notice that that version of R has joules listed. So 8.314 joules per mole per Kelvin is the one you want to use for these types of calculations. So do not use 0.08206, which has units of liters and atmospheres per Kelvin per mole. So that other version of R, that would be used if you were using the traditional ideal gas law calculation, PV equals nRT. But under these conditions, where you're using delta G equals negative RT natural log of K, the R value that you want to use is 8.314 joules per mole per Kelvin. All right, another important detail is that the units of R are joules per mole per Kelvin, but the units of delta G are usually given in units of kilojoules per mole of reaction. So just like we saw earlier in this video when using the Gibbs free energy equation, and the delta H and the delta S had different units, you have to pay close attention to units when you're using this equation. Now, T, the temperature, is the temperature at standard conditions, and that would be 298 kelvins. So be careful with the signs of your numbers in your calculations and your final answer, and I'll show you what I'm talking about when I talk about signs by using this example calculation. So in this example calculation, we are given the chemical equation for a certain reaction. It says 2SO2 plus O2 produces 2SO3, and we are told that the delta G at standard conditions for this reaction is negative 142 kilojoules per mole of reaction. We have to calculate the value of the equilibrium constant K. Remember that the equation delta G equals negative RT natural log of K, that equation is listed on the AP Chemistry equations and constant sheet, but the rearrangement of that equation where you solve for K, that equation is not listed. So you have to know how to do that rearrangement. And so that rearrangement, getting K on a side by itself, looks like the one that's featured on this slide. So K is equal to the letter E, which is the base of the natural log, and it's raised to the power of a ratio. And that ratio is negative delta G divided by RT. So notice that there's a negative in that ratio. So E raised to the negative delta G over RT, that means that if delta G is already negative, it's negative 142, I have to remember that a negative times a negative is a positive, so that's why I did not list the sign of negative in my ratio. Also, you'll notice that R has units of joules, but if delta G has units of kilojoules, you have to fix that problem. So what I've done there is I have multiplied by 1,000 to go from kilojoules to joules. So on the top, applying the negative sign, I have 142, and then I multiplied by 1,000, so it's 142,000 joules per mole of reaction. And on the bottom, I have the ideal gas constant, the proper one that I'm supposed to use with this equation, so 8.314, and I have joules per mole Kelvin. I multiplied by 298 Kelvin because that's the temperature at standard conditions. So the ratio, when done properly with the proper units, is 142,000 divided by 8.314, also divided by 298, and that ratio is equal to 57.3. So E raised to 57.3 power is a very large number. It's 7.67 times 10 to the 24. Now, this is a very large value of the equilibrium constant K, indicating that this reaction essentially goes to completion. Remember that one of the essential knowledge statements is that processes where delta G is negative favor the products. That is, the value of K is greater than 1, and this certainly applies. We have a negative 142 kilojoules per mole of reaction for the delta G, and we have a very large value of K. All right, now let's move on to question 19 in the packet. So what you're doing in question 19 is you are given 4 different chemical equations for different reactions, and then either I give you the equilibrium constant K and you calculate the value of delta G, or the other way around. I will give you the delta G in units of kilojoules per mole of reaction, and then you calculate the value of the equilibrium constant K. In addition to the calculations, the question you have to answer about each of these equations is, are reactants or products favored at equilibrium? And we can answer that question right now without doing any of the calculations, because we know from that essential knowledge statement that processes with a negative delta G favor the products, that is, K is greater than 1, and processes with a positive delta G favor the reactants, that is, K is less than 1. So in the first equation that shows the dissolution of solid silver chloride, AgCl, we are given that the value of K at 298 kelvins is a very small number. It's 1.8 times 10 to the negative 10. So since K is less than 1, the reactants are favored at equilibrium. So the AgCl solid is favored. In the next equation, between carbon monoxide, CO, and water vapor, the value of K at 298 kelvins is a large number. It's 10 to the 5th power. So when K is greater than 1, the products are favored. Now for the next 2 equations, we're not given the value of K, but we are given the delta G. So in that third equation in the table, where N2 reacts with O2 to produce NO2, the value of delta G is positive. So a positive delta G, that equilibrium favors the reactants. And then the last equation, where C2H4 plus hydrogen produces C2H6, has a negative delta G. And that would favor the products. That's thermodynamically favored, so kind of toward the right. Now, let's go ahead and do the calculations to solve for the missing information in this table. So if I'm given the value of K, which is 1.8 times 10 to the negative 10, I'm going to go ahead and use the equation delta G equals negative RT natural log of K. So I've got my negative sign. I've got the proper value of R, which is 8.314 joules per mole Kelvin. I've got my temperature of 298 kelvins, and I've got the natural log of 1.8 times 10 to the negative 10. So when I do that math, I get positive 55,600 on my calculator, but the units are joules per mole of reaction. So I have to divide by 1,000 to go from joules to kilojoules. So the answer is positive 55.6 kilojoules per mole of reaction. All right, well, hopefully that calculation made sense to you. Let's move on to our next calculation. So for the next equation, we are given that the value of K at 298 kelvins is 1 times 10 to the 5th power. So delta G equals negative RT natural log of K. So there's the negative sign. There's the 8.314 joules per mole per Kelvin. I've got my temperature of 298 kelvins and the natural log of 1 times 10 to the 5th power. So when I do that math on my calculator, this time I get negative 28,500 joules per mole of reaction. I will divide by 1,000 to go from joules to kilojoules, and I get a value of negative 28.5 kilojoules per mole of reaction. So the value of delta G is consistent with our prediction that when K is less than 1, we have a positive delta G, and when K is greater than 1, we have a negative delta G. Now let's move on to our next calculation, where we are given the delta G and we have to solve for the value of K. So this time I will use that rearranged version of the equation. So K equals the letter E the base of natural log, raised to the power negative delta G divided by RT. So watch out for sign and watch out for units when you set up this calculation. So there's my ratio. So even though the delta G is positive 103, I'm applying the negative sign in that ratio, and I'm also turning that number from kilojoules to joules. So that's why I have negative 103,000 in the numerator of that ratio. So that's negative 103,000 joules per mole of reaction. And on the bottom, I have R times T. So I have 8.314 joules per mole Kelvin, and then I also have 298 Kelvin, the temperature at standard conditions. So that ratio works out to be negative 41.6. And when I take the E on my calculator, the base of the natural log, raised to the negative 41.6 power, I get a value of K, which is 8.58 times 10 to the negative 19. Now, if you did this calculation and you got a slightly different number than what I got, it's possible that you kept the number into your calculator or you rounded differently, but hopefully you do realize that we're expecting a very small value of K. Because we have a positive delta G, K should be less than 1, and it is. But there could be slight variations in what you get in your calculation depending on how you round your numbers. Now let's take a look at that last calculation. We have a negative delta G, so we are expecting a value of K that is greater than 1. So again, here's the rearranged version of the equation where I'm solving for K. So I have E raised to that ratio negative delta G over RT. Because I'm applying the negative sign, a negative times a negative is a positive, that's why I have 101, but it's 101,000. So I took negative 101 kilojoules per mole, I applied the negative sign in the ratio, and I turned kilojoules to joules. So it's 101,000 joules per mole of reaction. On the bottom, I have that same setup with R times T, so 8.314 joules per mole Kelvin times 298 kelvins. And so that ratio of negative delta G over RT with the proper units works out to be 40.8. So E, the base of natural log, raised to the 40.8 power, gives me a very large value of K, which I was expecting since this is a negative delta G, so K should be greater than 1. I get 5.24 times 10 to the 17 power. Now, if you got a slightly different number than what I did for your value of K, when you did this calculation, you might have just rounded a little bit differently, but hopefully you understand how to solve for K if you're given delta G, and how to solve for delta G if you're given the value of K at standard conditions, 298 kelvins. All right, now it's time to take a look at our next topic in this packet. This is topic 9.6, free energy of dissolution. Here are some essential knowledge statements from the AP Chemistry course and exam description. The free energy change, or delta G, for the dissolution of a substance reflects a number of factors. So the context here would be dissolving a solid solute in something such as water or a liquid solvent. So we have the breaking of the interparticle attractions that hold the solid together. That would be the solute that's being dissolved. And then we have the reorganization of the solvent around the dissolved species. And then we have formation of interparticle attractions between the solute particles and the solvent particles. It is possible to estimate the sign and relative magnitude of the enthalpic, in other words, referring to enthalpy, and the entropic, referring to entropy, contributions to each of these factors. However, making predictions for the total change in free energy of dissolution can be challenging due to the cancellations among the free energies associated with the three factors cited. Now, this will make more sense when we see a specific example, and that will be coming up in number 20. But first, I'd like to talk about the details of delta H as well as delta S. So first, delta H. The change in enthalpy, or delta H, represents the change in energy, usually in the form of heat, that is associated with a physical or a chemical change. If delta H is positive, energy is absorbed by the system. Breaking attractive forces between particles is an endothermic process. On the other hand, if delta H is negative, energy is released by the system, so forming attractive forces between particles is an exothermic process. Now take a look at the particle diagrams below. So if attractive forces are broken between particles, then the delta H for that process from left to right would be positive. You're breaking attractive forces, energy is absorbed. But now imagine you're going in the opposite direction. So now attractive forces between particles are formed and the delta H is negative. We can do a similar story to talk about the delta S for such a process. So the change in entropy, delta S, is related to changes associated with the dispersal of matter and or energy. Entropy increases when matter becomes more dispersed and the particles have more freedom to move around. The number of possible arrangements of the particles increases, and also energy is dispersed. For example, the temperature of a sample of matter increases, resulting in a broader distribution of the kinetic energies of the particles. Now, if delta S is positive, then the particles of matter are more dispersed and more disordered, and there is a greater number of possible arrangements of the particles. So delta S is positive, more dispersed, more disordered. On the other hand, if delta S is negative, now the particles are less dispersed and more ordered, and there's a smaller number of possible arrangements of the particles. So looking at that same particle diagram that I showed you for delta H, if we start with a solid and then the particles become more dispersed and have more freedom to move around, the delta S for that process from left to right would be positive. So entropy is increasing. But if we go in the opposite direction, now the particles become less dispersed and more ordered, the delta S is negative and the entropy would be decreasing if we go from right to left. So again, just to summarize, we have delta H and delta S. If delta H is positive, energy is absorbed by the system. Breaking attractive forces between particles is an endothermic process. On the other hand, if delta H is negative, energy is released by the system. Forming attractive forces between particles is an exothermic process. And with respect to entropy, if delta S is positive, the particles of matter are more dispersed, more disordered. There's a greater number of possible arrangements of the particles. On the other hand, if delta S is negative, the particles of matter are less dispersed and more ordered, and there's a smaller number of possible arrangements of the particles. Now, before we take a look at question 20 in this packet, this diagram might look familiar to you. I actually did introduce this particular diagram back during Unit 6. It was topic 6.1 on endothermic and exothermic processes. And what you're seeing is step 1, step 2, and step 3 for the process of dissolving a solid into a liquid solvent such as water. So in step 1, what you're seeing are attractive forces that are being broken as the particles of the solute are broken apart. We can talk about entropy, but we can also talk about enthalpy. So breaking attractive forces would be a positive delta H. The particles are more dispersed, so that would also involve a positive value for delta S. So positive delta H, positive delta S. Now in step 2, it's kind of similar in that we are breaking attractive forces, but now it's among the particles of the solvent as opposed to the particles of the solute in step 1. So we're breaking attractive forces between the particles of solvent. The particles are becoming slightly more dispersed, so we have a positive delta H and a positive delta S for step 2. Now step 3 is the opposite of steps 1 and 2. So instead of breaking attractive forces, as you can see, we now have a process in which we're forming attractive forces. We're forming attractive forces between the particles of solute and the particles of solvent. So that would be a negative delta H for forming attractive forces. And hopefully you can see that now the particles are less dispersed and more ordered as they come together. So that would be a negative delta S. So step 1 and step 2, positive delta H, positive delta S. And then step 3, negative delta H, negative delta S. So I've pretty much given away the answers to question 20, but let's go ahead and take a look at it. So the particle diagram shown above had been presented in Unit 6. It represents 3 different steps describing particle level events that occur when an ionic solute dissolves in a polar solvent such as water. So in question 20, use the information in the diagram above to fill in the missing information in the following table. For delta H and delta S, indicate the sign as positive or negative for each change. So steps 1 and step 2 are going to be the same answer all the way across. Are the attractive forces between particles broken or formed? So they're going to be broken in step 1 and step 2. The delta H will be positive. The particles are becoming more dispersed in steps 1 and 2, and the delta S is positive. Now step 3 will have an opposite answer compared to steps 1 and 2. So in step 3, the particles are forming attractive forces. The delta H is negative. The particles are now less dispersed or more ordered, and the delta S is negative. So hopefully the answers to question 20 make sense to you. And now it's time to move on to our next topic in this packet. This is the last topic in this packet. This is topic 9.7, coupled reactions. Now, these 2 essential knowledge statements for topic 9.7, they are taking 2 different approaches to solving a particular type of problem. And that problem is, what do you do if there is a thermodynamically unfavorable process? How can we get that process that is thermodynamically unfavorable to occur? So the first essential knowledge statement implies that we're going to add an external source of energy. So it says, an external source of energy can be used to make a thermodynamically unfavorable process occur. Examples include the following: using electrical energy to drive an electrolytic cell or charge a battery, or using light to drive the overall conversion of carbon dioxide to glucose in photosynthesis. Now, the next essential knowledge statement involves combining 2 different chemical reactions together, and that process of combining reactions together, that is known as coupling, or a coupled system, so coupled reactions. So that essential knowledge statement says, a desired product can be formed by coupling a thermodynamically unfavorable reaction that produces that product to a favorable reaction. For example, the conversion of ATP to ADP in biological systems. So in the coupled system involving at least 2 different chemical reactions, the individual reactions share 1 or more common intermediates, and the sum of the individual reactions produces an overall reaction that achieves the desired outcome and has a negative value for delta G. So when delta G for the overall process is less than 0, then the overall process is thermodynamically favorable. Now, when you add 2 reactions together, if that sounds a bit familiar, back in Unit 6, you learned about something known as Hess's law, where you added equations together, and then you also added the delta H values together. So coupling reactions together is going to feel very similar to the process known as Hess's law. We're just going to apply that to delta G as opposed to delta H back in Unit 6. All right, let's take a look at question 21. In part A, it says, the reaction represented by the equation shown above, and we can see a positive delta G, so that would be not. So it isn't thermodynamically favored to occur because the sign of delta G for the reaction is positive. Now, in part B, I see a negative delta G. So in part B, the reaction represented by the equation shown above is thermodynamically favored to occur because the sign of delta G for the reaction is negative. So could we couple these two reactions together in such a way to produce an overall process? By combining these two reactions together, could we create a thermodynamically favorable process? Let's go ahead and take a look at question 22. It says, in the space below, show how the two chemical equations from question 21 can be combined together to produce the overall chemical equation shown above. Notice that the overall chemical equation shown above does not have a delta G value. So that means we're going to have to figure that out. By combining these two equations together, we can combine the delta G values together. So again, this process is similar to what you did during topic 6.9, Hess's law. So what I'm going to do is write the two equations, one on top of each other. This was from question 21. And now when I add the two equations together, notice how there's sulfur on the right in the first equation, and there's sulfur on the left in the second equation. So I can cross those out on opposite sides. That would be the common sort of intermediate or substance that is common to both of these reactions. And now when I add these two equations together, it matches exactly what I can see at the top of this slide. So what's the delta G for this overall process? It would be the sum of positive 86.2 and negative 300.4. And so when I do that math, I get negative 214.2. Calculate the value of delta G for the overall chemical equation, which we just did. Is the reaction represented by this equation thermodynamically favorable? Yes, the reaction is thermodynamically favorable because the overall sign of delta G for this overall reaction is negative. So back to that second essential knowledge statement, the sum of the individual reactions produces an overall reaction that achieves the desired outcome and has a delta G that is negative. So just looking at getting the copper sulfide, Cu2S, to produce copper and sulfur, that wasn't favorable. But if we can combine that with another reaction that is favorable, in which sulfur reacts with oxygen to produce sulfur dioxide, then the overall sum of those two reactions coupled together produces a process that is thermodynamically favorable. All right, now let's take a look at one more example of coupled reactions. This is question 23. It's also the last question in this packet. So in part A, it says, in the space below, show how equations 1 and 2, shown above, can be combined together to produce equation number 3. So I'm going to go ahead and write equation number 3 down near the bottom part of this slide. And then I will take a look at either equation 1 or equation 2 to determine, do I need to reverse any of these equations? Do I have to multiply all of the coefficients by a certain number? Let's go ahead and take a look at the details of equation number 3. So the first chemical I'm going to focus on is on the left side of equation number 3. I see 2 moles of Fe2O3 solid. Now in equation number 1, I also see 2 moles of Fe2O3 solid on the left, which means I don't have to do anything to modify equation number 1. I can simply rewrite that equation exactly as is. So the delta G is positive 742.2 kilojoules per mole of reaction. Now equation 1 with a positive delta G is not thermodynamically favored to occur. But maybe if I combine equation number 1 with equation number 2 in a certain way, I can get an overall chemical reaction that is thermodynamically favorable with a negative delta G. Let's take a look at the next chemical that I see in equation 3 on the left side of the equation. And that would be 3 moles of solid carbon. So notice that equation 2 has solid carbon on the left, so I don't have to reverse equation number 2. I want carbon to be on the left side of the equation, but I need a coefficient of 3. So I'm going to go ahead and multiply equation number 2 by 3. I'll multiply each of the coefficients by 3, and I will also multiply the value of delta G by the number 3. I'm going to rewrite that equation. So now I have coefficients of 3, 3, and 3, and then look at my delta G value. It was negative 394.4 kilojoules per mole of reaction, but when I multiplied that value by 3, I got negative 1,183.2 kilojoules per mole of reaction. I'm going to cross off the oxygen, which appears on both the left side of the equation and the right side of the equation, so 3 moles of O2 on the left, 3 moles of O2 on the right. And now I'm simply going to add these two delta G values together. So positive 742.2 plus negative 1,183.2 gives me a value of negative 441.0 kilojoules per mole of reaction. So we have accomplished that particular goal, which is to produce an overall chemical equation with a negative delta G that is thermodynamically favored to occur. So in part B, it says calculate the value of delta G for equation number 3, which we've already done. That's negative 441.0 kilojoules per mole of reaction. And then, is this reaction thermodynamically favorable? Yes. The reaction is thermodynamically favorable because the sign of delta G for this overall reaction is negative. So we basically took an equation with a positive delta G that is not favorable, involving this conversion of iron oxide, Fe2O3, into iron and oxygen. We coupled that with another reaction in which oxygen reacted with carbon to produce carbon dioxide, and that was favorable. So the combination of those two processes, the coupling of those reactions, produces an overall process that is favorable. So again, that is at the heart of that second essential knowledge statement for topic 9.7, that the sum of the individual reactions produces an overall reaction that achieves the desired outcome and has a negative delta G. So again, this was the last question in the packet, so we have come to the end of this video. I hope that you found all of these answers and explanations helpful. Thanks for watching.